Okay, sorry about the abrupt stop on the end, but I knew that I had a meeting that I had to attend, and I got interrupted on that one and thought I wouldn't get through. But anyway, here we go. Logarithmic differentiation. Very cool, very sneaky. It's kind of like Calcula Ninja work here. So let's be a calculus ninja. Logarithmic differentiation. Well, we've talked about derivatives of logarithms and such, so I guess maybe we'll just introduce a logarithm to this. Hey, we're working in calculus now. We're going to deal in ln. So I'm going to take the ln of both sides of this, and I get ln y equals ln sine of x to the x. And why might we use logarithmic differentiation on this? Well, the same reason if we were equation solving, we might be trying to deal with logarithms. Logarithm allows us to take this x and put it out in front here. So I get ln y equals x ln sine of x. And now let's take the derivative of both sides. So I'm just going to emphasize that. Now we're taking the derivative, and now we're using implicit differentiation. The derivative of ln of y with respect to x wants to be 1 on y, but there's an inside function of x here. We need dy dx. And this logarithm is a product rule. I'm going to have to write fairly small here in anticipation of what's going to happen to us on this, but I want the first function times the derivative of the second, and the derivative of ln sine of x wants to be 1 on sine of x, but there's an inside function sine of x, so we're going to multiply that by its derivative cosine x. So we're just treating the baby here. Plus, derivative of x is 1 times ln sine of x. That's our dy dx. Maybe you don't even need the extra room. But well, it's not really dy dx, it's 1 on y times. So I'm going to multiply both sides by y after I clean this thing up. In fact, I think I'm going to do it while I clean this up. So dy dx equals, let's clean this term up. Cosine divided by sine is cotangent, so this is x cotangent x, but I'm multiplying both sides by y, so that's times y, plus y times ln sine of x. So there's my derivative with respect to x. There's my derivative, but I got these y's in there. And if I could replace those y's, that would be optimal, because I would rather not have to, let's say I'm trying to find the tangent line of this at the value of x equals 3, whatever, 3 radians, I guess. So I'd have to put 3 in here, 3 in here, 3 in here. Oh, now I got to go back and put 3 in here and figure out what goes here. But dy dx, what I'm not crazy about is these y's. I wish I could have those in terms of x, but y equals this in terms of x. Therefore, dy, I guess I put a spot for it down here, dy dx could equal, in place of y, sine x to the x times x cotangent x plus sine x to the x ln sine x. Or if you like, we could have left that factored out. Maybe that's a back of the book answer. Sine x to the x times, what would I have had here? Nothing really else that I can factor out. X cotangent of x plus ln sine of x. So again, you got to be kind of led to it, and I'm led to it a little bit by this variable x, function of x raised to an x. I'd love that x to be out in front and just be able to deal with product rule here. Okay, well, this one doesn't jump out in that respect, but remember logarithms, there's property of logarithms that let us do a whole lot of pretty cool things here. One thing I might want to do even is take both sides to the 5th. Then I'm going to have a y to the 5th. Maybe I'm going to leave that 5th alone here. I'm going to write small again just in anticipation. But let's imagine if we weren't doing this thing logarithmically. If we weren't doing this logarithmically, I might write this all to the 1/5, which I might still do. And then I'd have 1/5 this big mess to the negative 4/5, and then times the derivative of this. And the derivative of this would be low d high. Ooh, d high is this times the derivative of that plus that times the derivative of this. Oh, this might be a chain rule. Minus high d low. Well, that's a chain rule. Oh, you see where we're going with this? Well, I'm going to just take the author's word for it and say, well, maybe doing some ln work would be good here. Now, at the same time, I'm going to be thinking of this all to the 1/5 power, okay, rather than 5th root of. So I get ln y. When I take this ln, is it clear? I hope it is, because you can't reply to me because this is a video and I can't see you. I hope this is clear. The 1/5 comes out in front. I'm not taking the derivative yet, but when I take the ln of something to a power, that 1/5 comes out and can come out in front, and I get x minus 3 squared times x squared plus 1 all on 2x plus 5 to the 3rd. Maybe you can see it now. If all of this was raised to the 1/5, I can pull that 1/5 out in front. Well, let's just keep working with properties of logarithms here. So this is 1/5 times, I think I'm going to need a bracket here. Any factor in the numerator can become addition of a new ln. So that's ln of x minus 3 to the 2nd plus ln of x squared plus 1. Any factor in the denominator of a single ln can become minus ln of 2x plus 5 to the 3rd. And in fact, I can pull this 2 out in front, pull this 3 out in front. If I like, distribute the 1/5. I'm not going to. 1/5 times, I get 2 ln x minus 3 plus, this is just ln x squared plus 1, minus 3 ln 2x plus 5. Well, I'm doing a whole lot of honors pre-calculus or pre-calculus and not doing much calculus yet. So is it time for us to think about taking the derivative of this? Perhaps. And I'm not going to write big here because I'm not exactly sure how much room this guy is going to take. Maybe it's worth doing that 1/5, or maybe it's worth treating all of this as though it was over 5. I don't know. Maybe I could leave the 1/5 out in front. So anyway, if I was to treat this like this, when I take the derivative, low d high, okay, the derivative of the high, it's bad, minus high d low, oh, d low is 0. Okay, so it's just going to be 1/5 times or all of this on 5. Let's see where we go with that. I think I might regret that, maybe leave that 1/5 out in front. But anyway, let's take derivative of both sides. Derivative of ln y, so I'm just going to go, I'm in calculus mode now. That was all blue. That's all pre-calculus. Calculus mode. Derivative of ln y wants to be 1 on y, but that's times the inside derivative, y is a function of x, dy dx. Equals. So is it clear? All I have to do is take the derivative of the top and leave that on 5. Or the 1/5, as I've said a number of times, constant multiples survive. So the derivative of this guy, the constant 2, survives. ln x minus 3 wants to be 1 on x minus 3, that's times the 2, times the inside derivative, but the inside derivative is 1. Oh, that's not too bad. Plus, derivative of ln x squared plus 1 wants to be at 1 on x squared plus 1 times the inside derivative, but the inside derivative is 2x. Wow, that's pretty good. Minus 3, ln of 2x plus 5 wants to be 1 on 2x plus 5, but times the inside derivative. The inside derivative is 2 times 2. And all of that is just being divided by 5. All right, what should we clean up here? maybe I'll just introduce those 5's into my denominators. So we've still got 1 on y, dy dx is just a little cleaning up here. 2 on 5, x minus 3 plus 2x on 5 times x squared plus 1 minus 6 on 5 times 2x plus 5. And that is what 1 on y dy dx is. But I would like to multiply both sides by y because I really just want to know what dy dx is. But y is this big messy thing up here that I'm going to call star. That fifth root of. So we get dy dx equals 2 star on 5 times x minus 3 plus 2x star on 5 times x squared plus 1 that's red, minus 6 star on 5 times 2x plus 5. And if star is that big mess, again, let's put it down here real quickly just so we can get a good look. If star is that big mess up here, star equals fifth root of x minus 3 squared times x squared plus 1 on 2x plus 5 squared. Just imagine replacing this in place of this, and that guy. And there's our derivative. That guy's a mess, but typically, understand, we're not going to be finding derivatives just to find derivatives. We could now put values in there, and we could figure out what this value, let's say we wanted the derivative when x is 1, or the slope when x is 1. We could now put 1 in here, get a value, and just put that value here, here, here. Okay, so, yeah, it was a mess, but we knew it was going to be a mess, and if you think that's a mess and there's an easier way, I couldn't encourage you more than to go ahead and try to find the derivative of this guy with that fifth root in there through chain rule with quotient rule. The quotient rule has 2 chain rules in it and a product rule in there. And we got to take 2x plus 5, quantity of third to the 6th, and all that, and see how long it takes you to simplify to get back to something that's going to be as nice as this, even with those ugly stars in there. So pretty darn slick, compared, especially considering we don't really often just care about finding the derivative. The derivative is just a tool for us to find slope. Okay, so with that, should be equipped to handle everything in 4.4a. Sorry for the abbreviated cutoff of the last video, but that's when I knew I had to be going to a meeting. I didn't think I was going to have time. So anyway, there you go. There's 4.4. That is the last section of chapter 4. Hope we can just destroy this test. We've averaged almost nearly 91% on the last one. Let's set that as our benchmark, and let's go beat it.